Hello. In this video, what we're going to do is take a look at using a student's t-test to analyze two sets of data using Microsoft Excel. Okay, so for the purposes of this example, we're going to use some salivary cortisol data from our human physiology lab in the fall 2022 semester. And so the data is already entered into Microsoft Excel. Excel is open on the screen right here. And so we've got samples from 15 students, so students 1 through 15, with an AM salivary sample and a PM saliva sample. And then these are the salivary cortisol levels that were calculated using an ELISA analysis. And so we've got the AM samples, the PM samples. Within this, we've already calculated the average and the standard deviation. So what we're interested in trying to determine is what is the difference, or is there a difference between these two samples? And so I'm just going to click on a cell over here. We're going to use the function property, or the function command within Excel. And so if we click on this little F sub X up here, insert a function, we click on this and this automatically gives us an equal sign within the box right there, and then a whole variety of different tests that we can use. I've used the t-test fairly recently, and so it's present there. If it's not there, you just clear the search for a function command and put t-test and click on go, and you see it gives us all the t-tests right there. Double click on this and say, or double click or OK, and it gives you kind of a window that pops up here that asks you for the data that's necessary in order to be able to run your t-test. So the first things that it asks for are going to be relatively simple. It's going to ask for array 1, which is basically your data for 1. And so in this case, we'll click on that box, and then we can go over and left click on our first cell, drag back down, and so we're going to collect the data for students 1 through 15 for their AM saliva samples, and this gives us all the cells within B2 to B12. We release the left mouse button, and it has entered that data automatically there for us. The second array is going to be the PM samples, so we do the same basic thing. We click on the first box, holding the left mouse button down, drag through and collect all of the data within this. When we release this, this takes us back into the function arguments, basically programs Excel to do the t-test for us. Then we go down here and it asks for the number of tails. Tails then becomes a little bit more complicated. So we need to think about what it is that we're going to be doing in this type of analysis. So in this case, again, instructions within Excel say the tails specifies the number of distribution tails to return. A one-tailed distribution equals 1, a two-tailed distribution equals 2. That's great if you know whether or not you need a one-tailed or a two-tailed test. So we're going to take a step back and figure out which we want to look at underneath this example. So basically, in any statistical test, you have the option to check between a one-tailed test and a two-tailed test. And so this is what is illustrated on the slide here. We've got our expected mean here based on our hypothesis, and we're looking at results that are either overestimated or underestimated. With a two-tailed test, we are looking at whether or not there is going to be a difference between the two groups of data that we're studying, but we're not saying that there's going to be a direction to that difference. And so we're looking at saying, is there a difference either at that kind of overestimated, that high end of the range, or is there a difference at that underestimated low end of the range? So we're not looking at whether or not this effect is going to be causing an increase or a decrease. We're looking at whether or not there is going to be a difference. The two-tailed tests are always going to be more conservative than a one-tailed test. So if you're at all uncertain, it's always appropriate to do a two-tailed test if you do not have evidence that there is a direction effect in your experiment. Now, the alternative to a two-tailed test is a one-tailed test. Again, this is used to determine if there is a difference between the two groups being studied, but there is an assumption of a direction effect. Now, when I say assumption, it means that you have prior knowledge indicating that there would be a direction effect. And so if you're looking at the effects of fertilizer on the growth of a plant, you would expect that the fertilizer is going to promote growth, and you would have evidence then, prior knowledge, that there is likely to be a direction effect. With this, we can then look at one end of the curve. We can look at a one-tailed test, and this is going to give us more power and more precision because we're only looking at one side of the null hypothesis expected results and looking at whether or not there is this direction effect. Now, please keep in mind that if you are not confident that there is going to be a direction effect, if you do a one-tailed test, you increase the likelihood that you are not going to accurately analyze your results. Okay, so based on what we talked about with the one-tailed versus two-tailed test, there is good evidence that the salivary cortisol levels are going to be higher in the day than they are at night. And so we could say that we are going to be doing a one-tailed test, but I'm going to assume that we don't necessarily have that information. And so I'm going to put a conservative two-tailed test in there. So I just enter 2 into that box, and again, it updates our formula there, and then it gives us the final argument within this calculation down here, type. It says type. Type is the kind of t-test, paired equals 1, 2 sample equal variance equals 2, or 2 sample unequal variance equals 3. And so this is, again, something that we need to determine prior to running our t-test for our experimental results. So to understand whether or not we're going to use a paired or an unpaired t-test, what we're looking at is a paired t-test is that there is some type of natural pairing in the results being analyzed. And so the example we've got here is basically the same subject with a sample in the morning and the same sample in the afternoon. And so we're basically testing the same group and the same subjects twice. And so in this case, the example up here on this slide is a pre-test, intervention, and a post-test. This would be an example of a paired t-test. We're looking at, again, the same group at different times like we're doing within this experiment. And so the pre-test, post-test situation is going to be a good example of a paired t-test. Now, we need to understand what are the other types of t-tests as well. Now, the two-sample t-tests are this idea that you're going to have a population, or at least a sample of the population that you're going to be looking at, and you're going to randomly assign those individuals either into one group or another group. A two-sample t-test is also referred to as an independent two-sample test. So in this case, we've got 2 examples. We've got 6 subjects that are available for our study. We are going to randomly assign 3 of those subjects into a group that receives a treatment. So they basically receive the intervention. And we are going to assign, again, randomly 3 of those subjects into a group that does not receive the intervention. And so this is, in essence, a control group. And so an example of this would be, we've got 6 plants. We are going to take 3 of those plants and provide them with the intervention, provide them with the treatment, so provide them with fertilizer, and then we would have another 3 plants that are down here that are receiving water alone. And so that's an example of a 2-sample t-test. Another example of that would be taking a look at the average height of male students compared to the average height of female students. And again, there are going to be different individuals, different subjects in the 2 different groups. So that identifies whether or not we're going to be doing a 2-sample group, basically looking at 2 groups. But it doesn't identify whether or not we are going to be looking at that equal variance or unequal variance. So with the equal variance, the idea is that we have basically the same amount of variation in the observations between the intervention group and the control group. And so when the variance is known to be equal, we can do a 2-sample equal variance test. Now, the way that we determine that is basically more math. And so if you are not sure if there is going to be equal variance, what you need to do is run an unequal variance test. And so an unequal variance test, a two-sample unequal variance test, is basically looking at the fact that in some situations we would have greater variability in our observations versus another group which has less variance or less variability. Now, the slide I've got up here is looking at the amount of time it takes to do a 1 mile run. Athletes that are conditioned are probably going to be running in a much less variation in their times, where non-athletes with variable levels of endurance and training and basically preparedness to run a mile is going to have a much greater variance. And so you're going to run a two-sample unequal variance test if the variances are not same, or if you're not sure if the variances are going to be the same or not. So based on this experiment, we already know that we are looking at the same individuals with two different samples separated by time. So we're going to be doing AM samples and PM samples. So this is going to be a paired t-test. And so we're going to enter paired equals 1 here. We enter 1, hit return or OK. And this is going to give us the p-value right here. This gives us a p-value of 0.004. You can continue with the decimal points, but it's not necessarily. Okay, so this is great. We have done a student's t-test to look at our results. We've got a p-value of 0.04. Now, what does that mean? So in order to understand what that p-value means, we need to review very quickly the difference between the acceptance region and the rejection region. And so the acceptance region, we're basically looking at whether or not our observed results are similar enough to our expected results based on our null hypothesis that we are going to be accepting our results as being due to chance alone. And so basically this acceptance region is going to be taking a look at our mean based on our hypothesis generated expected results, and we're going to be going plus and minus 1.96 standard deviations of that null mean. Now, the 1.96 standard deviations basically means that we're going to be looking at 95% of the observations that could be occurring in relationship to this mean. And so we're looking at this central point, and then basically half of 95% above that mean, half of 95% below that mean. And we're going to say basically that if our statistics are showing us a result within that area, it is going to be considered likely if our null hypothesis is true, and this is going to correspond to a p-value greater than 0.05. Now, the rejection region is basically the region underneath these tails, on the extreme region, kind of away from the mean based on our expected results. Now, the rejection region is going to be looking at those observations that are so extreme that they're greater than that 1.96 standard deviations away from that null hypothesis, meaning that these are values of our results, the test statistic, our t-value, in the case of what we're doing here, are going to be considered unlikely if our null hypothesis is true. And then in this case, we're going to have p less than or equal to 0.05, meaning that our results are going to be so extreme or so unlikely to occur, they're going to occur less than 5% of the time, less than 1 time out of 20, if our null hypothesis is true. So when we use this information for decision making, we basically have two situations. If our p-value is greater than 0.05, this p-value is telling us the probability that our observed results will occur if the null hypothesis is true. So if our p is greater than 0.05, it means that our observed results will be in the area underneath this curve, the area of these possible results that could be true if our null hypothesis is true 95% of the time. What we're going to say then is that any variation we see in our observations in relationship to the expectations are likely to be caused due to random chance alone. And so with a p-value greater than 0.05, we're going to accept the null hypothesis, and basically accepting the null hypothesis means that there is no difference between the group and that the independent variable has no effect. Now, the alternative to the p-value being greater than 0.05 is a p-value that is less than or equal to 0.05. Again, the p-value is going to be indicating the probability that our observed results will occur if our null hypothesis is true. If our p-value is less than or equal to 0.05, this means that the observed results will be in this region, this 5% of the region. If we're doing a two-tailed test, the 5% of the region, 5 divided by 2, so the 2.5% of extreme results at the low end, and the 5% divided by 2, the 2.5% of the results at the extreme upper region. And again, remember, we're looking at p less than or equal to 0.05. We're looking at dividing that in two, basically because we're looking at those extreme results at the high end and the low end in this example when we are using a two-tailed test. Again, this means that the observed results will be in this area, in the area in red, less than 5% of the time if that null hypothesis is true. And so if our results are falling at this extreme region, then the variation of the results is unlikely to be due to random chance alone. And so with a p-value less than 0.05, we are going to reject the null hypothesis. And if we reject the null hypothesis, that means we are going to accept our alternate or research hypothesis. The overall effect of this is that there will be a difference between the groups and the independent variable has an effect. So when we put all of this information together with our sample example right here, we've got our AM sample with a mean of 20.4 plus or minus 2.6 nanograms per mil. Our PM sample had a mean of 14.9 plus or minus 5.2 nanograms per mil. We had a p-value based on our two-tailed paired t-test of 0.04, and we can summarize that as saying we have a p-value less than or equal to 0.01. 0.05, or in this case 0.01, a little bit more significant difference between the groups. In terms of decision making, we're looking at a p-value less than 0.01. That means that there is less than 1% of a chance that the results we are observing in this experiment are due to random chance alone if that null hypothesis is true. That means that we are going to reject our null hypothesis, and in the act of rejecting our null hypothesis, we are going to be accepting our research hypothesis. So to apply or use this decision in describing our results in a paper or a poster or a presentation, what we're going to do is use our means. So the AM sample mean of 20.4 plus or minus 2.6 nanograms per mil. Our PM sample had a mean of 14.9 plus or minus 5.2 nanograms per mil. And using our t-test, we calculate our p-value as 0.004, which we can abbreviate and basically round off as being p less than or equal to 0.01. Now, we are going to describe the results in words, and so we can have a sentence that looks something like this. The AM salivary cortisol sample, in parentheses 20.4 plus or minus 2.6 nanograms per mil, close paren, was significantly higher. We can make that statement based on the fact that we ran the statistics. The statistics showed p less than 0.05, which means that there will be a difference between a group, and that difference is significantly or statistically significant. And so the AM cortisol levels were significantly higher than the PM salivary cortisol levels, open paren 14.9 plus or minus 5.2 nanograms per mil, and then we add the p-value in the sentence as well to provide the evidence that we ran the statistics, and the statistics show that there is a true statistically significant difference between the two things that we're comparing here. In this case, we're going to put p less than or equal to 0.01 and then close paren and close the sentence out. So hopefully this helps you with understanding both how to do a t-test in Microsoft Excel, as well as what that information means and how we can use that information in a written lab report or a poster or any description of your results. Thank you and have a great day.